Okay, so good evening, everyone. Again, welcome back to this lecture series, which are being organized by the India-based Neutrino Observatory project. And I'm sure many of you have been following for the last many weeks on very interesting talks on this. And of course, we are now ready for another super interesting talk, if I can say that. And before even I introduce the speaker formally, I must, on behalf of you, must thank him, as I just now mentioned, to take up giving this lecture at extremely short notice. Person Neelmani could not give this talk today. He is going to give this on Monday, that's on 17th. Professor Amol Dighe is going to talk today on neutrino detectors and the physics they teach us. In case you wonder that, similar or whether such talks were held in this series or elsewhere, I can tell you that he is going to give a rather different, new and very interesting perspective of the detectors from what he calls from a phenomenologist's point of view. So I think it is going to be much different than what you would have heard about the detectors per se and also the physics per se, that given respectively by, let us say, experimentalist and phenomenologist. Okay. And to say a couple of more words about Professor Dighe, is of course a professor at the Tata Institute of Fundamental Research from the Theoretical Physics Group. And his main areas of interest are, of course, high energy physics and astroparticle physics. His aims to understand the nature of fundamental interactions by studying properties of detectors. Amol, can you hear me?
Yes, now yes.
Yeah, I think there was kind of reboot of Zoom, maybe
Mhm.
partly missed, but nevertheless, okay. So with those few, so, let us request Amol for his another very interesting talk on neutrino detectors and the physics they teach us. Amol.
Okay, so thanks a lot, Satya. So, of course, as those who know me know that I'm essentially a theorist, not experimentalist. And in fact, I see that in the audience, there are many people who perhaps know about detectors much more than I do. So, of course, no, they are always welcome to come, stop me, and make their comments. I will anyway stop many times during this talk to ask for questions because it is perhaps good to have halts and get things clarified rather than going ahead at a constant pace. So my talk, as Satya mentioned, is not going to be about neutrinos. It's actually going to be more about principles behind neutrino detectors as I understand them. So this is, of course, in that sense, a limited view. And while doing that, we'll also learn a bit about the story of neutrinos, but the focus is going to be on detectors and various techniques that have been used in order to detect neutrinos of various energies and coming from different sources. So I guess because of this online series, which has been going on for a long time, many of you are familiar with neutrinos. So I shall assume a certain amount of basic familiarity. But let me anyway try to remind you of where we get neutrinos from. So of course, there are natural sources of neutrinos. Sun is the largest source of neutrinos that we have. We have neutrinos which are produced in the Earth's atmosphere because of cosmic rays. These two I will discuss a lot during my talk. There are neutrinos that are produced inside supernovae. We have seen them once in 1987, and hopefully we'll see some more in our lifetime. There are astrophysics accelerators. like active galactic nuclei, for example, from which we may have seen some neutrinos so far. I will mention them at some point of time. Standard cosmology tells us that because of the Big Bang, there are so-called relic neutrinos, which are present everywhere in the universe, and the density is about 330 neutrinos per centimeter cubed. We have not been able to see them yet. However, no, if standard cosmology is correct, that's what we should be able to see. Neutrinos are also produced artificially. Nuclear reactors produce a lot of them, and particle accelerators also produce a lot of them. So our aim now is to look at these neutrinos and see how they can be studied. The neutrinos that I mentioned just now actually cross a very wide spectrum of energy. So on the x-axis here, you see energies going from almost micro electron volts to 10 to the power 18 electron volts. So this is almost 24 orders of magnitude. And the sources that you see initially, there's a big peak called cosmological neutrinos. These are also called as Big Bang or relic neutrinos. When you go to energies of the order of MeV, you get into solar neutrinos, then supernova neutrinos, and reactor antineutrinos. Around energies of hundreds of MeV to GeV, you start getting neutrinos from the atmosphere of the Earth, which occupy a rather wide range. And as you go to higher energies, you get neutrinos from active galactic nuclei or other astrophysical sources. And at very, very high energies, you could get what is called as GZK neutrinos. So what are motivations for detecting these neutrinos? Okay? Apart from the fact that they exist there, therefore we should know what they are. We do want to understand nuclear reactions happening inside the sun. We want to observe neutrinos produced in the Earth's atmosphere and see what they do. We may want to monitor nuclear reactors and radioactivity of the Earth itself. We may want to observe astrophysical phenomena, and we may want to test the standard models of particle physics and cosmology. So if you're interested in any of these 5 things, then being able to detect neutrinos of some kinds would be of interest to you. Of course, there is a big problem with neutrino detection, and that is that they interact extremely weakly. So for example, let's take one of the big detectors that we have currently, take supercaviocande. It is about 50 million liters of water. The number of neutrinos passing through this detector every day is about 10 to the power 25. However, the number detected every day is only about 10. Okay? So this tells you that the efficiency of any detector to detect neutrinos is very, very small. And therefore, we always need very large detectors which run for a very long time. So I divided neutrinos into a few catchy phrases. I called them discoverers, sun seekers, earth watchers, beam catchers, skygazers, and something new. So let's go through these one by one, and we'll see what it is. So let's look at discoverers first. And in this, I will try to describe the experiments that detected the 3 kinds of neutrinos for the first time and the ideas behind them. So this is the first ever detection of neutrinos, which happened in 1956. Note that Pauli had come up with the idea of neutrinos in 1930. Okay, so this is an experiment, a successful one that has happened after 26 years after the prediction of neutrinos. Okay. It was called as $1 million particle because the budget for the experiment happened to be of the order of $1 million. So what's the idea here? We know that neutrino detection is very hard because efficiency is very small. For this reason, the first thing we should do, we should go very close to a neutrino source. And for that, these people went very close to a reactor. As a result, you get reactor neutrinos, which are antineutrinos essentially, and we denote them by nu E bar. Note that at that point of time, it wasn't known that they're antineutrinos. It was not known that they are of the electron kind. In fact, it was not known that there are different kinds of neutrinos. So now what's the detector? Detector is actually a scintillator detector. And what it does essentially is provide 2 elements. Firstly, it provides protons because there is hydrogen in the scintillator. A nu E bar interacts with proton to give a neutron and a positron. Now this positron loses a bit of energy and then annihilates with another electron somewhere in this scintillator. As a result, you get 2 photons of energy around 0.5 MeV, because the essentially masses of E plus and E minus get converted into photons. Okay? So the first signal that you are going to get are 2 photons of energy approximately 0.5 MeV. The second thing that happens is this neutron. This neutron gets absorbed onto cadmium. This cadmium then becomes 108 cadmium becomes 109 cadmium star, which is the excited state, which again decays via emission of a gamma. Now, because this step process take time, this gamma comes slightly after the first 2 gamma. So now we have got a signal which is 2 gammas of 0.5 MeV each. This is mega electron volts, and 1 gamma of a similar energy, slightly lower, but which comes slightly after this. Okay? So the detector therefore was water. Job of water was to provide essentially protons, and then the mix to this was cadmium chloride, and the cadmium chloride was the one that acted as neutron absorbers, and to detect these photons we had used scintillators. Okay, so the idea of Reines and Cohen, who got Nobel Prize for this in 1995, was essentially this. So this was the first discovery of a neutrino in 1956. Once the discovery was made, at that point of time, people figured out that this will solve the beta decay problem of energy, loss of energy. Okay, so which means that in the nuclear reactions, actually energy momentum are conserved. Okay, and it's just that energy that you do not see goes out as neutrino. People were very excited, and as a result, experiments started on looking at other nuclear reactions or other particle physics reactions in which some energy is lost. Now, one such reaction was the decay of pi meson. So pi meson, as we know now, goes to a muon and a neutrino. Of course, if you don't detect neutrino, what you will see is that a pi meson goes to a muon and nothing else. And in this reaction, you see that energy, law of conservation of energy seems to be violated. So therefore, one suspects that perhaps there is a neutrino here, because now we know that neutrinos actually exist. Steinberger, Schwarz, and Lederman had this experiment at Brookhaven, where a proton beam came and produced pi mesons, and these pi mesons decayed in flight. The detector that was used basically was a spark chamber, in which when a neutrino went, the idea was at some times it will interact, will produce a charged particle, most likely electron, because you expect this to be the reaction, right? Nu bar plus nucleon, giving you some other nucleon plus electron. So they expected that you will find positrons inside this spark chamber. A nice tidbit here to tell is that this steel shield that you see, which was used to get rid of background, was actually obtained from the steel of Second World War submarine. That just a nice information, a nice trivia to know. Okay, so these people expected to find a positron and therefore declare that pion decays actually produce neutrinos. What they observed was something very, very strange. They observed not a single positron, but they observed quite a few muons. Okay, and in fact, that led them to conclude that this must be a new particle, which is not electron neutrino, but a muon neutrino, because it is associated with a muon. For this discovery, they got Nobel Prize in 1988. So this is our second discovery detector, which, as you see, is essentially made up of this steel shield and a spark chamber, such that whenever a charged particle passes through this, because things are at high potential, this will ionize the gas inside this chamber, and it will produce whatever sparks or charges, which will be detected by his detector. The third neutrino that was detected was, of course, tau neutrino. Whereas the discovery of electron neutrino was very long awaited, 25 years, and the discovery of muon neutrino was very serendipitous, in the sense it was not expected at all. The discovery of tau neutrino was kind of expected. In fact, if you were around in 2000, you perhaps wouldn't have noticed any big deal about this. Okay. The reason is that we were very confident about the standard model at this point of time, and we knew that new tau has to exist. Even in that case, just looking and confirming that indeed a new tau exists is a commendable job. So what does this detector do? What you want to see is a new tau reacting with a nucleon, giving you tau and some other nucleon. And this tau is then going to decay via these processes. So when this tau decays, this tau will either decay to electron, and so it will produce either electron nu e bar, muon or nu mu bar, or a pair of quarks. Okay, so basically a shower of hadrons. So since now you want to see a tau, which is a lepton, these E and mu, which are also leptons and the hadrons, the detector now needs to be have more elements and do more things. So this detector, for example, was made up of many parts. The initial part was emulsion target, okay, and that's where you expect the neutrino to come, interact, and start a tau, and maybe you will be able to see this tau track for a very, very short distance. And to do that, you need emulsion. After this, you need to detect electrons, muons, or hadrons. For that, there are drift chambers, there are calorimeters, and these will be able to detect mainly electrons as well as the hadrons. Muons, on the other hand, since they will not lose the energy so quickly, will be able to pass through and reach this detector which are at the far end. And these long tracks will tell us that a muon was produced. So this was a detector that needed many stages, because you need to observe a tau, a muon, a hadron, or electron shower. So as you try to go to the slightly complicated decays that you want to reconstruct, you want to make big detectors. Note that the detector already is about 15 meters long. Okay. So this was all about the discoverer neutrinos, discoverer detectors. I would invite people maybe to ask questions, or if you have any comments, or no, if I goofed up something, I think people are welcome to correct me. Are there any comments here?
I think there was a comment posted on the chat. You can probably see from Professor Tatar. Do you want me to read, or you can?
Yes, maybe I will read it. This is a comment from the Datar. He said that Davis first put the chlorine detector near a reactor and did not find any 37 argon. And the conclusion was that his detector could detect neutrinos and reactors do not emit them. So these were all attempts which were made before Anderson Cohen. There was also an experiment by Schwartz, who had a proposal for detecting new beam from pi r. Of course, I'm not going to talk about everything that happened. I have just chosen a set of detectors that I thought would be interesting, that I know something about. So, but thanks for this call.
Yeah, sure.
Yeah. Next, I'll go to detectors that I call as sun seekers.
I'm sorry. There is one question from Shailesh. Let us take that before you move.
Hello.
Yeah.
Yeah, my question is, sir, the electron neutrinos were detected way earlier than the muon neutrinos, and still the Nobel Prize took another 10 years after the Nobel Prize of muon neutrinos. So is there a particular reason for that?
There is no such cause and effect in when you discover and when you actually get Nobel Prize. So it's definitely a non-scientific question. So let us skip that. Bindu has a question. Yes, Bindu.
Okay. Yeah, I just want to say that this whole delayed coincidence technique with the gamma rays is an extremely clever technique. And it is so clever that over the last 90 years, how many years? Over the last 50, 60 years, it is still the technique used. It is still, so it is tested, it has tested so many tests. I mean, it has stood the tests of many experiments, and still the delayed coincidence, detecting the two gamma rays after 10 seconds, the delayed coincidence is really a marvelous technique. is what I wanted to say. And nobody ever marvels at it as much as I do. I think it's amazing.
Thanks, Bindu, for that comment.
There was another question from YouTube. It says, why was cadmium chosen?
Because of this reaction. See, many times you will find when you talk about nuclear reactions that to understand neutrinos, you need to understand nuclei. Okay? Cadmium was chosen especially because it undergoes this reaction. Okay, it absorbs neutron, is called as a neutron absorber, goes to an excited state and gives out a photon. For the delayed photon technique that Bindu just mentioned about, this is required. Okay? So you need to be in search of nuclei which can do this, absorb a neutron and give a delayed photon.
Amol, can I just comment here?
Sure.
Okay. This particular isotope of cadmium has a huge cross section for absorbing neutrons. So with only a fraction of a percent of cadmium chloride, you can get a very good efficiency for absorbing the neutron. The proton can also absorb it because water has protons, but then that cross section is way down. It's only about 0.3 barns. Whereas this is about hundreds of kilobarns.
Yes. So right now, of course, Super Kamepand is also looking at using gadolinium, but I think I'm moving ahead of my talk. So I will come to that when I. Okay. So now I'll move to what I call as sun seekers, which are essentially the detectors that look at solar neutrinos. Okay? So the energy, the solar neutrinos is essentially from keVs to about 10 MeVs, so which you will see here. Although we normally say that in the sun, protons combine to give helium, it actually happens through many stages, which are actually depicted on this page. Don't have to look at all the reactions in detail, but notice that you start with proton-proton or proton-proton-electron, and by chain of reaction, finally you end up going to helium. On the process, you produce electron neutrinos of various energies. So if you see in this process, it is energy below 0.4 MeV. This process has 1.4 MeV. Here it is 0.86 MeV. Here it's 0.3 MeV, and here are the spectra of energy which go to quite a high value. So if you look at the spectrum of solar neutrino looks something like this. Okay, so now the question was how to detect neutrinos which have energies of the order of few hundreds of keV to about 10 MeV. You will see the shading here in light, slightly dark and dark blue, but I will come to that later after the next two slides. So one of the first experiments, and perhaps the first one, to look at solar neutrinos was by Ray Davis, who got Nobel Prize in 2002 for this. This was a radiochemical experiment in the sense it used radiochemical reactions of nuclei. The material used here was perchloroethylene, which is a cleaning fluid. And a reaction that was looked for was the reaction of electron neutrino with chlorine, and which was supposed to give argon and an electron. This detector was a detector which was a huge tank, and after a few weeks, I think it's about 4 weeks, that you would actually take out all the material which was in this detector and try to look for argon atoms. Okay. So the argon atoms, although I think were radioactive, had a very large half-life, and therefore would last for more than a month, and therefore this tank would be emptied after about a month, and literally number of individual argon atoms were counted. Okay, so you could imagine in this huge tank, finally you end up locating some small number of argon atoms. So clearly, one disadvantage of this was that there was no energy measurement, and you would not know exactly when the neutrino came and interacted. However, this was the first detection of solar neutrinos, for which later on Davis got Nobel Prize. And this was again the experiment that went on for many years, and also was the one that confirmed that indeed there was a solar neutrino problem. So chlorine was again one of those nuclei that were identified, which would be useful because of this reaction. Another nucleus which was identified was gallium. And indeed, the experiment that used gallium was called as GALEX. And it had a very similar principle. Gallium chloride was used essentially as the target material. The electron neutrino interacted with gallium to give you germanium, and you basically take out this liquid through this filter that you see on this side, again after a certain number of days. Again, therefore, you did not know when the neutrino interacted, and you could do no energy measurement. However, the threshold of this reaction is 0.233 MeV, and therefore, if you detect germanium nucleus, it tells you that the energy of incoming neutrino was more than 0.233 MeV. In the case of chlorine, this was slightly higher, and I have written it here. However, you would see it in this particular plot. Okay, so gallium threshold was 0.233 MeV, which means that beyond this line, everything to the right of this would be detected by gallium, but you would not know what the energy is. Okay. Similarly, chlorine, which you see is about 0.8 to 0.9 MeV, it would detect all the neutrinos with energies which is more than about 0.85 MeV or so. The last detector of solar that I talk about is Super Kamiokande, which is of course running even now. For those of you who haven't seen this picture before, this is a detector which is a water Cherenkov detector, which means that the main material which you see filled here is actually water. It's a huge detector. It has about 50 million liters of water. To get an idea of this size, you will see that this is a boat, and this boat has 3 men sitting in it. They are cleaning up this set of photo tubes on this side, and these photo tubes, I don't know if you can see me, are essentially of this size. Okay. So right now cleaning is going on, but the water will of course rise. They will fill the water. The people in the boat will of course come out safely, and then the detector will start. Now, what this detector does is this detector detects electron neutrinos by looking at its interactions with electrons. Okay. So NUI interacts with electrons. It's a reaction in which this electron now gets energy because of its collision with the incoming neutrino. This electron is therefore started moving very fast. If the speed of this electron is more than the speed of light in water, then it would give what's called a Cherenkov light or a Cherenkov light cone. So this Cherenkov light would be detected by these photomultiplier tubes. Okay, so note that now this mechanism is very different from what we had earlier, because now when an individual event happened, we detect it almost immediately, okay, within in fact a few nanoseconds. Secondly, by looking at the properties of this Cherenkov cone and how long it lasts, can actually determine the energy of this neutrino. So this detector now is able to detect the time of arrival of a neutrino, as well as it can, to a very good extent, estimate its energy. Okay, so that's one advantage over the earlier radiochemical experiment. On the other hand, its threshold is much higher. It's about 5 MeV, because this is not based on the threshold of this reaction, but it is based on how much of the Cherenkov light, which is emitted, can be collected by the photomultiplier tubes, and you would be able to say definitely that this light is coming from an event and is not a bad one. Okay. So the reason for a threshold and the reason for its being able to take energy tells you that this is a very different kind of detector than the earlier. So if I just go back a few slides, you will see that the Super Kamiokande detector can basically measure neutrinos only in this last dark blue line. So energy range is smaller. However, the other advantages more than outweighs. So what happened because of this? What Super Kamiokande can do it could measure the number of neutrinos at different energies. Okay? And in fact, this is a plot in which it has tried to measure the survival probability of the neutrinos, which is basically data divided by what is predicted by the standard solar model. Okay? And it observed that it is almost about 0.4 to 0.5 over its whole energy range. So we now have three kinds of detectors. We have chlorine detector, Galax and Sage are the gallium detectors, and Kamiokande, which is a Bottle-Cherenkov detector. The yellow bar that you see corresponds to what you predict by the standard solar model, and the purple bar that you see is what you have detected. So clearly, therefore, what you detect is much smaller than what you have observed. That is called a suppression, and that indeed was the solar neutrino problem. It told us that not only is the suppression, but different detectors give different suppression. Okay? And of course, we can imagine that that may have to do with the fact that they measure different energy ranges. To figure out if it's indeed true, if indeed the loss of neutrinos is because they're going into other kind of neutrinos, as was proposed by Ponte-Corvo and after that by other people, a very innovative detector was designed, which was called as SNO, or Sudbury Neutrino Observatory Detector. And this detector used heavy water Cherenkov. So the material was D2O and not H2O. How did this give an advantage? This gave an advantage because, as opposed to protons, the deuterium nucleus, okay, the deuteron, actually participates in different kind of interactions with different particles. So for example, deuteron, when interacts with mu E, can give a charge current interaction in which it makes 2 protons and 1 electron. Okay. This reaction is sensitive only to the flux of electron neutrinos. On the other hand, look at this blue part, the same deuteron can also interact with mu E, mu and mu tau, so neutrinos of all flavors, gives neutron, proton, and a neutrino, which of course you won't be able to see. But you'll be able to see this neutron and proton. This process, therefore, is sensitive to the flux of electron neutrino as well as the flux of mu and tau neutrinos. So what this means is, if our hypothesis is true, okay, by which I mean if it is true, the electron neutrino indeed goes into mu or tau neutrinos, this number should not change. The flux that is measured by this neutral current process should not change. On the other hand, flux measured by the charge current process should be suppressed. Indeed, this was observed. So you will see this blue band here corresponding to the blue process. And this blue band corresponds to exactly the flux as was predicted by the standard solar model. On the other hand, this red band corresponding to this red process essentially told that the number of the flux of electron neutrinos is less than the flux predicted by the standard solar model. A very nice thing was, of course, that since this was, of course, heavy water, it had lots of electrons also. You could also see the interactions of neutrinos with electrons. And it so happens that this reaction, which was the same that happened in Super Kamiokande, was sensitive to this combination, which is electron flux plus 1/6 of the flux of muon and tau neutrinos. And this happens because of various cross sections. And if you also plot this in your observations, it turns out that all these three intersect at almost one point, and this tells you that your observations are in fact consistent. And this basically convinced everybody that the solution for solar neutrino problem was that neutrinos go into something else. So therefore, coming up with the idea of heavy water was very, very important. Okay. Apart from this, the process of detecting the charged particle produced is the same, whether it is a H2O detector or a D2O detector. So now what has happened is, in addition to the first 3 bars that we already saw, we have these last 2 bars. The 4th bar that you see shows that when you look at charge current events, you will see a separation. Okay, many neutrinos are lost. But when you look at neutral current events, almost all neutrinos are found. In fact, within error bars, these two actually, the yellow bar and blue bars actually matches, and that tells you that you indeed have detected all kinds of neutrinos. Okay. So these sun seekers have then taught us something about neutrinos. They told us that, of course, neutrinos are essential for the sun to shine, so you produce nu E, but a flux was missing, and the reason was that neutrinos have different masses, and electron neutrino mixes with the others. And that's the reason that you get loss of neutrinos. Okay? Theorists also showed that you could explain that by taking into account the fact that the matter inside the sun affects effective masses and mixing of neutrinos, which is called an MSW effect, and the resonance that takes place inside the sun. Okay. However, we will not go into this because our interest is detecting neutrinos and not to understand their properties, at least in this talk. This solution of solar neutrinos was identified by a detector called as Kamland, which was a neutrino detector at Kamioka. This was again a detector which used liquid scintillators, and the idea that was used was that it would try to detect antineutrinos coming from many nuclear reactors in Japan. You will see these dots all over the place, and Kamland was detected here. It would look at neutrinos coming from all the sides. A liquid scintillator has some advantages over water Cherenkov, which is that it detects a larger number of photons. Okay, in fact, many tens of times more number of photons are produced per neutrino coming, and that makes it its energy resolution better than simple water Cherenkov. On the other hand, because inside this detector, scintillator detector, the electron actually scatters a lot, it is more difficult to determine neutrino direction. So again, every detector has its own plus and its own minus points. This is good for measuring energy, but not so good at measuring direction of neutrino. The Kamland was so arranged so that for the values of solar neutrino, values of masses and mass square differences, these neutrinos coming from the reactors, okay, would be lost, and that loss would be measured at Kamland. So in fact, it did actually finally prove that the values of delta M square, which was measured, which was inferred from the solar neutrino experiments, actually is the right one. Okay. So here ends my my sun seeker detectors. So maybe it's time to take some comments.
Yeah. So there are again quite a few. If you see on the your Zoom, there are a couple of one question and a comment. Maybe you can read, and I will after that I will take up questions from YouTube.
Yeah. So one is of course how do we calibrate the detectors? So of course it involves two things. It involves some understanding of how neutrinos should interact in the standard model with elements in the detector. Second part, which is actually the most important, is to look at the number of photons that come in the case of the water Cherenkov or scintillator or D2O detectors. In the case of radiochemical, it is just counting the number of new nuclei that have been produced. So this is of course, yeah, you need to know about your instrument very well, and you also need to know about how neutrinos come and what the cross sections are with the material we detect. The comment from Vivek Datta saying that while Pontecorvo was the first to propose oscillations, he, as well as many others, particle physicists like C.N. Yang, were skeptical of the solution for the solar neutrino problem. Indeed true. In fact, John Bacall, who was the person who predicted all the solar neutrino fluxes, was often very aggressively attacked by particle physicists, saying that maybe he and people who calculate solar fluxes don't understand the sun very well. So in fact, there was a fight among the three sides of a triangle. There were solar physicists, They were theorists and they were experimentalists. Okay, so either the solar physicists didn't understand the sun, or the experiment didn't understand detector, or the particle physicists didn't understand how neutrinos work. Okay. Turned out that particle physicists didn't understand how neutrinos worked, but once they figured it out, well, neutrino oscillations were discovered.
I have a question.
Sure. Yeah. So Bindu has a question.
Okay.
Her question is, before masses were known, how were oscillations conjectured, and whether the spin flip was a part of this. So I perhaps am not the best person to answer this. My knowledge of history is not so good. However, people, for example, knew of oscillations in the KK bar system around this time.
But those are massive also, na?
Sorry?
Neutrino was supposed to be massless. This is what
Yes.
always gets me. How did they think of oscillation? Pontecorvo, how did he think that
So
it could have
clearly,
oscillation?
even for Pontecorvo, of course, also when he first introduced oscillations, he tried to think of between neutrino and antineutrino, because at the back of his mind was K and K bar. But he knew that it did need a mass difference. So I do not know that anybody has proposed neutrino oscillations without neutrino masses in the early times. But if there is anybody else who knows, maybe they can tell me. But I think mass was a requirement for neutrino oscillations.
That's what I always thought.
Yeah.
Okay, Amol, there are quite a few questions. One or two I'm keeping it aside because I'm sure you're going to cover them a little later. But if gallium chloride was used in Galax experiment, was there also the probability of neutrino interacting with chlorine, also like in the case of Davis experiment?
So this is a good question, and I do not have an answer to this.
Okay, I'm sure there will be someone who will answer this. We'll get back, maybe Professor Datar. Another question from Sonali: in super K detector for very high energy of tau neutrino, can it make its charge cousin, that is tau1, at its minimum ionization energy range? Which Cherenkov light detection methods?
So whether you create tau or not mainly depends on what your energy of a neutrino is. Okay. So for example, to create a tau, normally I suspect you will need energy of neutrino, which is about 4 times tau mass would be my approximate guess. So I would say about 8 GeV or so. The neutrinos from the sun, of course, have very low energy. Okay? So solar neutrinos will not produce either muons or tau, because they are only a few tens of energy.
I heard Super K claims detection of tau neutrino, but via some other methodology called neural network mapping. Could you please tell about the neutrino detection techniques?
Yeah. Could you come to this towards the end? I think I will cover the now, and details. I think we'll have a long discussion after the talk.
Okay. There is a comment from Lakshmi. It says 3.5 GeV is the threshold.
So 2 times tau mass. Okay, fine.
Okay, fine. I think we kind of cleared the questions. Okay, and Professor Datar, the experiment was designed to separate 71 germanium. The main goal was to detect a signal from PP neutrino.
So this, I think, perhaps is an answer to this the gallium chloride question.
Okay, I think great.
Okay, so thanks. I think it is good that people who know and understand detectors more than I are commenting, because it's good if this talk becomes more of a discussion. I just try to guide this. So next I will go to earth watchers. And by that, what I mean is you essentially look at detectors that neutrinos that are produced on the earth, either in the atmosphere or inside the earth. So that's what happens in the atmosphere. When cosmic rays enter the atmosphere, cosmic rays are mainly protons. They will interact with the other nuclei in the atmosphere and produce pions. These pions will decay to muons and to neutrinos, and the muons further decay to electrons and neutrinos. So as you see in this diagram, some muons actually do reach the ground before they decay, but some of them decay high up and will produce neutrinos. There are two things that are typically known about this. These are not exact, but approximate relations. One is that at least for neutrinos that are coming from top, the flux of muon neutrinos was expected to be approximately twice the flux of electron neutrinos because of these two reactions that you see. Of course, this relation is not valid at all energies or at all angles, but this is approximately true. And the second thing was that if you look in any particular direction, then the number of neutrinos coming down would be nearly equal to the number of neutrinos going up along the same direction. At this time, it's good to take a diversion. And for those who are new to the game, just mention why is it that all detector neutrinos are underground. And one of the reasons is the cosmic rays. As you saw in the earlier reaction, in the earlier page, for example, you see that many of the muons actually reach the ground. It turns out that the number of muons and neutrinos reaching the ground are roughly equal or on the same order of magnitude. However, all these muons that will enter your detector will actually interact because they are charged particles, and normally a good detector detects almost all charged particles passing through it. On the other hand, only 1 in billions of neutrinos will interact. I put dots here because this number is dependent on the energy of neutrinos, and the number of zeros here would basically range from, let's say, 15 to 25, okay, depending on energy of neutrinos. So therefore, if you look at detector on the Earth's surface, the neutrinos get lost among muons because there will be so many muons being detected. When you go underground, the muons get absorbed inside the Earth, whereas neutrinos do not. Okay? And therefore, if you really want a clean environment for detection of neutrinos, you have to go 1 kilometer underground, or you go below a mountain so that on all sides you get about 1 kilometer of rock coverage. Okay. So coming back to what you want to detect in the case of solar, in the case of atmospheric neutrinos. So you want to see muon neutrinos and electron neutrinos because they are the two that are produced in the atmosphere. The detector that actually comes in very handy to do this is Super Kamiokande, the water Cherenkov that we already saw. And how can it do that? It can do that because we know that when the electron travels inside water, it scatters quite a bit. Okay. As a reason, the Cherenkov cone of electron that you see will be a diffuse ring. So as you see here in the left-hand side plot, this circle is just drawn for letting you imagine what this what the circle is. So the way to read this figure is that this is like a cylinder. Okay, this is the circular top, a circular bottom, and then you close this rectangle around itself so that it becomes a cylinder. And this circular shape is the Cherenkov cone that you see on the sides of the detector. In the case of muon, okay, because muon does not scatter as much, travels almost in a straight line, the Cherenkov cone that you see, this ring is quite a sharp ring. It is this diffuse versus sharp nature that actually tells us whether something is a electron-like event or a muon-like event. Okay? And in fact, the analysis of Super Kamiokande is always in terms of electron-like event versus a muon-like. So once you're able to separate them, since you're able to determine where they came from, you can make a plot of their zenith angle, which is this cosine theta, versus the fluxes. They also could determine energy. So they divided the neutrinos into sub-GeV electron-like events and multi-GeV electron-like events. And the right-hand side plots are sub-GeV muon-like events and multi-GeV muon-like events. And one thing you will very clearly notice when you look at this is that electron-like events are exactly on prediction. Okay? So red is prediction and the black dots are data. Electron-like events are almost bang on predictions, and muon-like events seem to be lost. Okay, they seem to be lost more when cos theta is less than 0, which basically corresponds to events that are coming up to the Earth. And this was what was called as the atmospheric neutrino puzzle. So finally, of course, the puzzle was solved. It was the neutrino oscillations, which required a difference in the masses of two neutrinos which participate in the mixing, told us that the probability of initial muon neutrino remaining a muon neutrino is given by this particular form. And as you see, as length increases, this second factor increases, and therefore the value of probability of finding a muon neutrino starts from 1 initially, but as length increases or the travel time increases, it goes down and up like this. The oscillation length is governed by what is called delta m square, which is the difference in the squares of masses, and that is why you need difference in masses. Amplitude of this is given by the mixing angle, and it's approximately equal to sine square. Okay. So for discovering this via superconducting observations, Professor Kajita was given the Nobel Prize in 2015. In addition to neutrinos produced in the atmosphere of the Earth, we also see neutrinos produced in the crust of the Earth because of radioactivity. So this plot that you see here is approximately what is expected to be the map of nu E bars coming from various parts on the Earth. Okay. Some of the dots that you see, the big dots, the small dots in the big background, are actually big nuclear reactors. But otherwise, here, blue color basically says that the number of nu E bars is very low, and as you go to darker colors, the number of nu E bars is very, very high. So as you see, along the continents, the concentration of radioactive elements is quite high. So you have uranium, thorium, or potassium, for example, and some of these things have, of course, very high concentration. The same detector CAMLEN, which was earlier used for confirming the solar oscillations, also came in very handy here because it has low threshold, can detect energies of neutrinos very well, however, does not have so much of a directional ability to detect this. So what it had to do is it had to measure the spectrum of neutrinos very well and then subtract out what was the expected spectrum of neutrinos coming from the reactors. So if you subtract that, then you will get the geo neutrinos. And therefore, of course, it's a very, very hard job since the energy range of reactor neutrinos is almost the same as energy range of neutrinos from the natural radioactivity in the Earth's crust. Okay. However, once we have more detectors doing this, we will understand Earth's radioactivity much better. This is, of course, INO, and I think most of the people in the audience don't need to be told about this. This is the future of atmospheric neutrino detectors. And the main feature of this, which is not there in any of the earlier ones I talked about, is that it has magnetized iron. What it means is when charged particles pass through this, they bend in different directions. Okay. As a result, you can distinguish mu plus from mu minus, or a positive from negative muon. Effectively, it means that you can distinguish a neutrino from antineutrino. Okay. So mu can be differentiated from mu bar, and you can now study neutrinos and antineutrinos of muon type independently. This again, it's proposed to be under a mountain inside a tunnel, and it will have about 1 kilometer rock coverage from all sides. Okay. So it has a structure of many layers of iron which absorb energy, interspersed with air gap in which we put scintillator detectors called as RPCs or resistive plate chambers. And the use of this is that we can also measure the energies of hadrons produced in the neutrino. So I'm sure you have already had many talks about this, so I will not go into details of this. But for those who haven't heard of this before, just remember that it is the largest, the most massive electromagnet built so far. It's going to be a 50 million kilogram or 50 kiloton weight of of this electrolyte. Okay, so I will stop my Earth watchers here and let me take expert comments or questions.
Again, I'm sorry, I'm always talking.
No, you are welcome. Yeah, please.
I was just thinking that since INO has lost so much time because of politics, it could concentrate on doing some really exotic, interesting measurements like neutrino magnetic moment. Nobody knows anything about the neutrino magnetic moment. Then spin flavor oscillations, then axions. Because of this, take advantage of this large magnetized detector, and look for these type of things which will make a significant contribution, because otherwise in the other fields it may fall a little bit far behind, but in these type of fields it may just make a big contribution.
Mm-hmm.
I don't know your ideas on this.
Yeah, I think perhaps this is not the time to go into this, but we will discuss about this later. Yeah. So in fact, people are thinking about different things that you can do apart from what the principal aim of INO is, and yeah, we will discuss that. But, I'm just only halfway through the talk, so these are nice ideas. We will take them up maybe in the discussion after. I see two more comments.
You want to see the chat?
Yeah. So I see this comment from Hariom, says directional information is not so good at Camden experiment, and then how such nice map was produced. So this map, I guess he's referring to this particular map. This is not a detected map. This is a calculated map. Okay, this is approximately calculated map, and this is not the number of neutrinos. This is by knowing about the estimations of radioactive elements in the crust of the Earth. Okay, this is not a major map. Vivek Datta made a comment. The Fukushima reactor accident resulted in all Japanese power reactors being shut, and this gave an opportunity to Camland to measure geoneutrinos with much smaller background. Okay. Sometimes unfortunate events can also be used to our advantage to gain our knowledge of science. Do you have any other comment?
Amol,
Yeah.
On the YouTube, there are a few questions. Sorry. What is the estimated flux of cosmic neutrinos?
I do not have the number right now on top of my head. In fact, perhaps Satya will know it better.
Maybe Professor Datar also will have them.
So the way to look at it, so there's of course a simple way to look at it, which is to go to this plot, which I keep on showing always. The cosmic neutrinos are this red curve. Okay, so it depends on what energy is. So you look at the energy, and at the energy, this gives you a flux in centimeter square per second plus the radius per MeV. So a number is very hard to give because it depends on what energy range you are going to. Yeah.
There are a few more questions. Can the neutrinos attain exact degenerate masses at certain energy scale?
I could not hear you well. I missed it.
Can the neutrinos attain exact degenerate masses at certain energy scale?
No, as far as we know, the neutrinos do not have degenerate masses because we see both solar.
So, another one. Actually, my question were okay. Maybe she was referring to a previous one. Actually, my questions were related to atmospheric neutrino energy ranges. Since threshold energy of tau production from tau neutrino is less than 4 GeV so far, so for atmospheric neutrino can produce tau 1. Did you
sorry, I missed it.
Yeah, I am also. It's not clear. Maybe. Okay, maybe we'll. I think I'm taking too much time to read this. You can go ahead and maybe we'll take up this and maybe another question later. And I also see something else coming up on your Zoom, Shailesh. So do you want to see that?
Yeah. So of course this is true. Antarctica is also radioactive, but as I will come to later, radioactivity gives you neutrinos of energies of the order of MeV or lower, whereas ice cube, as you will see, measures energies of at least 1,000 times more than that. Okay. So radioactive elements there in Antarctica will not affect detection because what the ice cube looks at is very different. But I haven't come to ice cube yet, so have some patience. Okay, so now I will go to what I call as beam catchers, and this is again just to people already know. There have been a few experiments that are so-called long baseline experiments. What it means is you produce a neutrino beam at an accelerator, and then you shoot the beam to a detector so that you can see or try to see what happens to the beam on its way during its long travel. So this top figure is the Japanese one, the experiment K2K, where you went from KEK accelerator to super Kamiokande, or in fact Kamiokamine, and from JPark to this was called as T2K, where the distance traveled is about 250 to 300 kilometers. There's the experiment in US. This is MINOS, but is also very similar to NOVA. The beam started at Fermilab and went to Sudan mine, traveled about 735 kilometers. And the third one is the Opera or Icarus experiment, in which the beam started at CERN and went to LNGS, which is the Gran Sasso National Laboratory. Now, here, the detectors used were of these kinds. Super Kamiokande, of course, is something that you already know. It's a water chamber detector, so I'll not go into this. For the MINOS detector, the detector used was essentially iron with scintillators. It's also a magnetized iron detector. However, it was about 5 kilotons, so about 10 times smaller than what INO proposes detector. The two detectors in the CERN to Gran Sasso beam were Opera. The Opera beam was the one whose one of the major aims was to look at the tau neutrinos, and therefore the structure is similar to what we saw in the case of donut, layered structure. You need, so this is where the beam comes, and then you have layered, you have a spectrometer plus a tracker, again a tracker and a spectrometer and so on, which actually help them to detect data. Icarus detector use liquid argon and what's called as TPC, which is time projection chamber. And in fact, in about a couple of transparencies, I will show you one picture about how a liquid argon TPC works. Okay. So again, here a beam entered in this direction, and we had a structure of using. So this, of course, this is iron. So this perhaps for neons, but this is the liquid argon part of Icarus detector. Okay. I will not show Icarus detector again, but I will show the proposed detector on Dune, which is also a liquid argon detector. So the future mega scale multipurpose detectors, and I will mention only two of them, which have already got going in some sense. At least they have been approved. So one is Hyper Kamiokande, which would be the big brother of Super Kamiokande. It is also a water chamber detector, just that its fiduciary volume is about 8 times bigger than the Super Kamiokande, which already was a very big detector. Okay. So you could see the size. The diameter is about 70 meters, and the water depth is also about 70 meters. Okay. So if you think of a building as with every floor of height of about 3 meters, it's about a 20 to 25 story building with a similar diameter. Okay, so it's a really large one. It will have more than 200 million liters of water. In fact, I think I'm wrong. It will be of the order of 3 to 400. But yeah. The second, so this detector, for example, will be used for an experiment called T2H, where the beam will be produced at JPark, and it will go to a detector, which is hyperconical. So instead of T2K, it will be called as T2. The second experiment, which has a different kind of detector, is called as Dune. Here, the neutrinos are produced at Fermilab, and they are passed through the Earth pass through almost 1300 kilometers. So it's really, really large distance. And they go to what is called as Sanford Underground Research Lab. And they're detected here at the FAR detector. This detector is what is called a liquid argon time prediction chamber. So what happens here? The charged particle travels and ionizes particles on the way. Let's say it produces electrons. Here, the vertical bars that you see, vertical and these electrons are the electrons, of course, from the liquid, from the argon atoms. To get idea of a size of the proposed detector, this is what you could see. This is a human being, and the detector will have about 30 kilotons of liquid argon. So again, liquid argon is used because of its properties, its cross sections with nu as well as nu. Okay, any comments about the beam catches?
And for some other need not be directly connected, but I think there is one on the question of delay in the Nobel Prize. I think that was asked before. Let me just have a look at on the why neutrinos in dune are fast in the trajectory, first uphill and then downhill. Okay. I think the picture that you have shown is
so, yeah. This is of course a bit exaggerated, but now you see when your distance between the source and detector is 1300 kilometers. Okay, then of course Earth's curvature has to be taken into account. Okay, so therefore they seem to be going in. Okay, maybe you're asking about this shape.
First Y up.
Okay, so this shape, I think, if I understand correctly, has to do with the way you want to create a neutrino beam. And I do not know. I think maybe somebody else knows this answer better, but it has to do with the way neutrino beam is being produced, about the accelerator.
Yeah, I think Amol, you are right. Basically, the beam line has to follow the hill, the slope of the hill, and that's an easier way of doing it, rather than drill a hole into the ground at that angle.
So that should do with the topography of Fermi-Land, essentially.
Yeah.
Okay, thanks.
Possible reason, okay. This, I guess, is answered.
With earlier things, so we'll come to that question later.
Okay. Yeah, I think for now we can move ahead.
Okay. Next, I will go to the stargazers, and that basically are detectors that look at neutrinos coming from the sky. So neutrinos are, of course, very good astrophysical messengers. A nice property is, of course, that they have no charge, so you don't bend the magnetic field. Therefore, they can point back to the source. Now, on the other hand, if you look at protons from cosmic rays, they don't point back to their source because they already have moved quite a bit in the magnetic field of the galaxy as well as the Earth. Of course, photons are the best in that sense because photons point back to the source. However, neutrinos have much lower obstruction or scattering than photons. So for example, neutrinos can also come from inside the stars, from which light cannot come. They can come from inside active galactic nuclei, from where light cannot come. They can come from inside supernovae, from where light cannot come. Okay, so therefore, neutrinos can arrive directly from regions from where light cannot come, and therefore give you another way or another window of looking at universe. While doing this, if you find interesting properties of neutrinos, well and good, but you already have neutrinos to observe the universe. What are the sources that we can observe? So firstly, of course, we can observe astrophysical phenomena that give a large neutrino flux, like a supernova explosion, for example. What happens in most of the astrophysical processes is protons get accelerated. These are called primary protons. Once they have become very high energy protons, they can interact either with the material of the source, or if they escape, they can interact with the CMB photons and produce pions, and these pions give us neutrinos. Okay, so accelerated protons almost always give you neutrinos. Sometimes they also give you photons if they give you pi zero, because pi zero give photons, pi plus minus give neutrinos. Neutrinos can also be produced by particle decays or nuclear reactions, maybe pair production and so on, in extreme environments. For example, like active galactic nuclei or in gamma ray bursts. So of course, you can identify neutrinos coming from one particular process. On the other hand, it is possible that over the lifetime of the universe, there have been many such astrophysical events which are given off neutrinos. And this flux has accumulated over the years. And you could see these diffuse fluxes of neutrinos. So which means that you do not see a flux of coming from a particular event, but average flux from such events that have been happening over last billions of years. So the detectors search for both of these kinds, direct detection as well as diffuse flux detection. And in this connection, one of the major detectors is this detector called an ice cube. Ice cube is well, sort of a cubical shape of size 1 kilometer by 1 kilometer by 1 kilometer. You can compare its size with the Eiffel Tower, which you see in this figure. The top here is South Pole. And the way you consider the detector is you obtain the ice for free because it is there at ice cube at the South Pole. If you go deep between 1400 to 2400 meters in this region, the ice is known to be very pure. It has less impurities. What you do then is you have your photomultiplier tubes, you tie them to a string, you tie many of them to a string, then you literally melt the ice and you try to lower your photomultiplier tubes along this string like this. So once one string goes down, you do it, of course, very slowly, taking care not to disturb the ice too much. Then you wait. The ice then freezes around these, and then this string with these photomultiplier tubes is now fixed inside the ice. You do it for many other strings, and then you create what you see on the right-hand side. These are many, many strings, and each of these black dots you see is a photomultiplier tube. Now, when a neutrino comes and interacts, produces a muon, for example, the muon is going to travel through this, and while traveling, it will emit some Cherenkov light, and that light will be detected by this photomultiplier tubes. The colors that you see here correspond to the time of arrival. So you know where it started first and where it went. So this is the basic principle of ice cube, and this is meant to detect high energy neutrinos. Similar detectors like this are also planned under the Mediterranean Sea, for example. This is a picture of a detector called Antares, not as big as ice cube, but still of similar size, and it is going to be expanded into what is called as KM3net. Again, you see these are photomultiplier tubes. They look like this on these modules. These modules are tied to strings, and these are buoys which keep these things floating on top and is anchored at the bottom of the ocean. Okay. So again, this is an array of photomultiplier tubes, and a charged particle passing through this will give Cherenkov light, which you will see at this photomultiplier. So for example, very vaguely speaking, muon neutrino will approximately leave a track that looks like this. The colors will give you the direction of travel, and the size of dots give you energy deposited. Okay, that's perhaps going into the details. If this is electron neutrino, or if they're hadrons, they will not form a track like this, but they will have a shower, in which case the energy will be spread sort of symmetrically in the small area around where the actual event has taken place. If it's a tau neutrino, not all the time, but at least sometimes, you get what is called as a double bang feature, in which the neutrino interacts, gives tau, and tau travels for some time and then decays, and you get two different showers which are separated by some distance. So this is called as a double band detector. So you could, in principle, have some information on the flavors of these neutrinos. Now, the problem with the detector, or the disadvantage about this, is that the photomultiplier tubes are actually rather far apart. Okay, so even here you see the distance between them is of the order of 14.5 meters. Even here, the distance is of the order of 20 meters. What it means is that if a charged particle stops traveling before 20 meters, then it can give its Cherenkov light, which reaches to only one of the detectors. Okay, which means that it's very hard to see that this is a track. So for a track to be found, the charged particle must travel a certain distance, and which means that this charged particle must have a certain minimum energy. As a result of this, the threshold of these detectors are of the order of about 100 GeV. Okay, in fact, they are made such that they are sensitive to energy above 100 GeV. And that goes back to the question which was asked some time back. So of course, radioactivity will not be able to make any difference. How high can you go? You can go as high as almost 10 to the power 16 electron volts. And the reason you can't go beyond this is actually very interesting. And that's because if your neutrinos are more than 10 to the power 16 electron volts, they actually get absorbed in the Earth when they travel a few thousands of kilometers. So we of course keep on saying that neutrinos pass through everything, but that is actually true for low energy neutrinos like solar neutrinos or atmospheric neutrinos, which are energies of the order of 10 to the power 9 GeV. This is 10 to the power 16 electron volts, 10 to the power 9 electron volts. This is 10 to the power 16 electron volts or 10 to the power 7 GeV. And at this energy, the cross-section of neutrinos is high enough that they actually interact inside the Earth and cannot reach the detector. So if you look at neutrinos that are going to come through the Earth, which are called upgoing, you will not see them beyond this energy. On the other hand, if you are going to look at neutrinos which are downgoing, okay, you can only see them for energies more than this, because below these energies, the atmospheric muon background that you saw is this should have been significant. Sorry, this last word is wrong. So below this, the atmospheric muon background is significant, and therefore you will not be able to distinguish neutrinos from the atmospheric muon background. So, so below this energy range, you can, above the energy range, you can see even downgoing neutrinos. Remember, ice cube is not, doesn't have a rock coverage of 1 kilometer. It only has a water coverage of 1 kilometer, okay, which is not strong. As you go to even higher energies, other detectors come into play, which are not built for detecting neutrinos. They're built for detecting cosmic rays. However, okay, so these are detectors which are essentially like OJ, which are basically meant for detecting cosmic rays. They are made up of scintillators or made up of fluorescent detectors. And the reason is because at such high energies, neutrinos can also interact in the atmosphere and give you giant air showers. And the cosmic ray detectors are precisely designed to detect such air showers. So all we have to do is to distinguish these air showers from the air showers produced by actual cosmic rays or the standard cosmic rays. Okay? So the way you do that is to try to look for those cosmic rays whose showers do not start near the top of the atmosphere, but actually start very deep in the atmosphere. So these are called deep downgoing muon showers. Because normal cosmic ray showers will interact at the top of the atmosphere because they are protons, but neutrinos actually travel way down. Okay, and that's the reason that using that you could distinguish very high energy neutrinos from the cosmic rays. Of course, detection has not been possible yet. We don't know of a concrete detection, but we expect that things will happen. Okay, and people do use those interesting techniques like looking for neutrinos coming which are skimming the Earth, okay, because a cosmic ray shower will not come skimming the Earth, or those that pass through mountains and so on and so forth. I think Perhaps this is not the time to go into it in detail, but these are some exciting possibilities. You can also detect neutrinos by using radio antennas. Okay, now it's again quite strange if you haven't heard it before, but there are experiments called as ANITA, for example, in which radio antennas are taken up by balloons. This is one of the antennas taken up by balloons, and you look at the South Pole. Now, what happens is, in case there is a deep particle shower, it actually produces something similar to a Cherenkov inside atmosphere, Cherenkov inside air. So this effect is called as the radio Askarine effect and can actually give you radio waves. And these radio signals could be detected by this radio antenna. So again, I mentioned this just because it's a very interesting thing that you could use radio antenna to actually detect neutrinos. Again, this can happen only at very, very high energy neutrinos, and well, there are no very clear indications of having detected neutrinos like this, although there could be some candidates. A very large source of neutrinos in the sky is actually supernova, which actually has very low energies, about 5 to 50 MeV compared to the other ones we discussed before. However, it is important to keep an eye on this supernova in the sky because it can identify neutrino mass ordering, okay, normally inverted when it comes. We can locate a supernova almost one day before the light arrives because neutrinos from a supernova start early and reach early, almost one day before the light. So it's possible, therefore, to by looking at neutrinos, predict that a supernova is going to be seen tomorrow in the sky in a certain location. Another thing you can do with a supernova is that you can track its shock wave by looking at neutrinos while the shock wave is still inside the supernova and the star has exploded. This is again not possible with light. Knowing this, in fact, many of the detectors that are currently active also act as a supernova early warning system called as SNEWS. Okay, and these detectors, which keep on tracking individual neutrinos, whenever they see a very large rise in the number of neutrinos compared to the usual rate, they give a combined signal together and try to see if that will correspond to supernova. A signal hasn't come yet. We haven't observed a supernova in our galaxy in the last 10 years since this has been active. But of course, whenever this happens next, I will get a signal on an SMS on my mobile. And you could go to SNews network and actually register yourself if you want such an instant message on your mobile that a supernova will be observable in the sky tomorrow. Very surprisingly, the Cherenkov detector like IceCube can also detect these neutrinos, although they are much smaller energy than what the threshold is. And the reason is, although individual neutrinos cannot give a signal, a large flux of them can give a signal, which is called as the Cherenkov group. So in fact, IceCube happens to be a very good detector for determining the luminosity of it. All of these detectors actually keep on look at different characteristics of supernova neutrinos. And in fact, I don't want to scare you, but want to show you that the reactions in water Cherenkov, scintillator, liquid argon, or lead detectors are very, very different and give you complementary information. So it's very important for obtaining information about many different aspects of supernova neutrinos and their spectrum. Okay, so this ends my Stargazers, and I only have a short thing to say about new ideas. I can of course see that I am going way, way over time. Let me ask Satya.
Yeah. Let us go ahead. And I don't see any more new questions per se.
Okay.
So
I just have a very quick comment about new ideas.
Okay.
As you see, the ideas that are used for various neutrinos were really completely different. Okay. So in this one slide, I will mention 3 ideas that have come in recent times, and on some people have started working, which are again completely different from what we are talking about till now. So, for example, one idea was using Mossbauer effect and looking at neutrinos. So the idea here is to look at the decay of tritium, okay, which produces helium, helium-3, and gives out nu E bar and electron, but this electron is a bound state. Okay, if you manage to have this reaction, then this neutrino will have a fixed energy, okay, or energy in a very, very short range, and this could be detected by another helium detector, helium-3 detector placed nearby, okay, which can now take this electron and make tritium. It has been shown that there is a resonance enhancement of almost factor of 10 to the power 12 if you manage to have your energies exactly aligned. And this could be done if these helium atoms, these tritium atoms are embedded in a crystal. Okay. If this is in fact done, the neutrino oscillations can be visible even on a tabletop. Okay. So this, of course, is a great technological challenge, but a very interesting idea. I think it was proposed by Professor Raghavan, who unfortunately passed away a few years ago. Another nice idea is to use detectors based on indium. Turns out that indium can react with electron neutrino to give out this electron, whose energy is very well calibrated compared to this nu, because indium is a very heavy element. Okay, it's very well calibrated. Now, what this does is that it can actually look at the solar neutrinos and look at the line spectra in solar neutrinos, which have never been seen. For example, the neutrinos coming from beryllium in the sun actually are monoenergetic. And if we can measure the energies very well, one will be able to probe, for example, the temperature of the core of the sun, about which we have no direct information. Okay. Again, there are technological challenges in purifying indium, but that's an idea that is that's very exciting. Remember, I also mentioned Big Bang neutrinos or relic neutrinos. Okay, detecting them is very difficult because the energy is very small. The energy is of the order of 0.1 milli-electron volt. It's not a typo. It's not capital M. This is small m. The energy is milli-electron volts, and as you have seen, the threshold of our detectors are actually of the order of KeVs or MeVs, so it's very difficult to detect them, not definitely from what we have currently. The idea that has come up and is being tried at the experiment called as Ptolemy is that you look at a nucleus which undergoes a beta decay normally. Now what you do is if this nucleus interacts with an electron neutrino, even if a very small energy, then this will get induced to undergo this beta decay faster than usual rate, and we will be able to observe this electron at its final endpoint energy. Again, we are very far from achieving any success in this. However, once we do this, this would be a strong confirmation of the standard model of cosmology. So I will actually stop here because I think I have gone way over time. But these are my final comments. I personally am a theorist, so I'm always impressed by the kind of thing experimentalists come up with and actually implement. The variety of techniques used in detectors of neutrino is really mind-boggling. And each of them comes up with its own physics concept, which is suited for its own specific purpose. What I've shown you in this talk is only a sample, and I have missed many of the detectors. I didn't even go to detectors which focus on, for example, reactor neutrinos. Yeah, so the kind of detectors that you have are really amazing. They have used ideas that combine nuclear physics, atomic physics, particle physics, chemistry, electrodynamics, material science, and concepts coming from many of these different areas. And as you saw in my last slide, there are still unexplored ideas that can help us probe the neutrino world even deeper, and that's a challenge for material science and technology development. So the idea of my talk, therefore, was not to tell you about the physics of neutrinos, but the physics behind detecting neutrinos. And I'm very happy that people did participate and giving comments. I hope that I will we'll have some more discussion on this following this. So so let me stop here, Satya. I think
Yeah.
we can take any
Okay.
questions.
So maybe I will save some time in avoiding my usual summary, which you did so wonderfully in your remarks, and I really like each bullet so well, including the bullet number 2, which from the physics point of view, it combines understanding of so many concepts coming from diverse fields. At the same time, also your fourth point, which says it also sets so many challenges that goes in building such large detectors. But once you did, it also kind of brings a lot of spin-offs into doing things which are far away from particle physics. I think it's a fantastic field, not only in the repercussions of what you discover at the core of neutrino physics, which has become really challenging these days, but also the way you do the experiments and the spin-offs are also equally challenging, I guess, both for physicists and engineers. So with that one comment, let us see the one from Shailesh. Maybe you can read yourself too.
So let me read the last one. So
Yeah.
the Shailesh asked, can we analyze the supernova neutrino events quickly so that corresponding light signals could be detected later by other detectors by pointing the detectors in that direction? So answer is of course yes. It is done in fact in a matter of minutes. This is the S news network that I talked about. So the detectors that I showed in the this slide actually exchange notes all the time. Whenever they see a larger flux of neutrinos, they will coordinate and see whether the large flux of neutrinos was observed by all of them, multiple of them, or only one of them. Once the large flux is observed by multiple detectors, it's almost sure that it was not background or a fluke. And in that case, a signal would go to not only optical telescopes, but also telescopes which look at ultraviolet, gamma rays, radios, in fact, all the frequency bands. So that will happen within a matter of minutes. And normally, neutrinos arrive at least half a day, 12 hours, 24 hours before a supernova happens. So you will know approximate region in the sky from which it will come, although you will not know the exact pinpoint, and you will not know when. But this when is going to be hopefully in the next day or so. Okay. It is also possible that you don't observe the supernova, in which case it means that you have located a supernova from which light did not reach us, or a supernova which failed to explode, for example. Okay? The shock wave could not explode the supernova, and we could also observe a supernova if, in neutrinos by the detectors that we currently have.
Okay, so let us do this, Amol. We have one question or comment in the Zoom and two questions I'll take from YouTube before the wrap up. So this is from Professor Datar.
No, this is just a comment on your last section. It is possible that someday we will have a detector which uses coherent neutrino scattering. That will make the detector for a similar event rate about 100 times smaller.
Yes, true. Yeah. So to expand on Professor Datta's point, what nuclear detection means that if you have a nucleus with a very large number of nucleons, then the cross section will go as A squared as opposed to A. If the neutrinos interact with it coherently. And in that case, the cross section obviously will be able to get larger number of charge current events from such interactions.
As I said, just a couple of questions from on the YouTube. Ramchandran, isn't neutrinos have small magnetic moment? If so, won't they bend in magnetic field?
Magnetic moments makes things precise in magnetic field, not exactly bend. Neutrinos have, well, hopefully we have measured it yet, have a very, very small magnetic moment. So they can precess, but they not bend. I think bending in magnetic field will need them to have a charge. There are limits put on magnetic moment of neutrino. Again, by using the fact that the solar neutrinos, they actually reach us using their numbers, and the fact that they would not have changed their spin while they're traveling inside the magnetic field inside the sun, for example.
And another one, how scientists are trying to detect sterile neutrinos and which type of detectors can be helpful in their detection?
So sterile neutrinos, essentially they are sterile. What it means is that they do not interact with whatever materials we have at hand. Okay, so therefore, by principle, by definition, in some sense, they can't be detected. However, that they are missing can be detected. Okay, so in principle, all the detectors that we have currently, okay, could be used. What you need is you need to have very precise predictions on how many neutrinos you should be able to see. Okay, and then if you do not see those many neutrinos, then it means that some of them may have gone to sterile. So a good example here would be the beam neutrinos that I mentioned earlier, uniform neutrino beams, because when you make neutrino beams, you have a reasonably good control on how many neutrinos you produce. So therefore, you know how many neutrinos reach at the other end. And therefore, if the number of neutrinos reaching here is less, then you could say that you have a surrounding. Okay. Of course, there are the main experiments where surroundings are detected are located not so far, but reasonably close by to the accelerator so that the flux is quite large.
Okay, I thought maybe I'll take just one last, though this is, maybe we can finish with this. Are neutrinos their own antiparticles and how do they get their mass?
Okay, so I think for answer to both of these questions, there is Nobel Prize ready. So we don't know answer to either of these questions, and both of them are very important questions. Okay? So let me just mention one thing, that we do not know if neutrinos are their own antiparticles. However, we can know this if we are able to detect a particular reaction called as neutrino-less double beta decays, and I happen to have an extra slide which shows what the reaction looks like. Okay, so this is a right-hand side reaction, in which case we get a double beta decay of a nucleus. So 2 electrons come out, but no neutrinos come out. Okay, this can happen only with this one antiparticle. There are dozens of experiments around the world which are going out right now, which are trying to detect this, but none has succeeded. Okay, so the answer therefore is not known. And answer to your second question also is not known. We do not know how neutrinos get their mass. We know how electron gets its mass, and we know that it involves the Higgs boson particle, but it is not certain whether neutrinos would get their mass simply by interacting with Higgs boson or not. There are some technical problems with this. They are not being a right-handed neutrino, for example, but perhaps this is not the right talk to go into.
Okay. Yeah, I think Amol, we are almost at 7:45. So you really did a massive kind of talk plus discussion. Thank you so much for taking your time. And also thank you very much, as you also said, for the participants. So Siddhartha, Bindu, and also all the students who have also made it very interesting by asking very pertinent and important questions and the comments that came from the experimentalists, etc. So once again, Amol, thanks a lot on behalf of all of us for taking this lecture on a very, very short notice, but did a wonderful job. Thank you so much.
That's okay. It was a pleasure.
Yeah, thanks a lot. So thanks everyone. Come back on Monday. We'll have Neelmani talking about very, very interesting latest results just came from LHCb. So that's at 6 p.m. on Monday on 17th. Thank you. Take care. Good night.